Hello students, welcome back again with another video. Mr. Pineda. Chapter 8 practically it's talk about central limit theorem, one of the most important theorem in statistics. So what central limit theorem practically has two conditions. One is that if a random variable x is normally distributed, then the sampling distribution of x bar is also exactly normal. What it's saying is that if you're coming from a distribution that is normal or data that is normal, your distribution is just going to make it more normal. Whereas condition number 2 here, it talks about that if a random variable x is not normally distributed, then the sampling distribution of x bar will be approximately normal as long as the sample size is larger than and greater or equals to 30. Now, here's a very important thing, because in chapter 2 we learned about Chebyshevs, where when we did Chebyshevs we had some distribution that was skewed left or skewed right, or unknown distribution. And at this point we don't want to go back and redo Chebyshevs. So if as long as the sample size is larger or equals to 30, then we can use our central limit theorem, which is going to be z equals to x bar minus mu divided by sigma divided by square root of n. So this distribution, we see that previously in chapter 7, but in chapter 7 practically z of x minus mu over sigma, it was only for one person at a time. We're picking practically 1% at a time, where here we can pick many at a time, which in a practical application in the real world, we don't want to concentrate in one rather than concentrate in many. So for example, if you were to invest money in the stock, you wouldn't put your money in one stock, rather you put your money in many stocks, so that will give you a higher probability of making money. Now, in order to really understand these two conditions, practically I had created RStudio simulation for you guys. So this is my colleague. He did a study at Cal State Fullerton, so I'm using his data. His name is Dr. Jamin Chedian. So I'm going to use his data to demonstrate my simulation of central limit theorem. So condition 1, we learned that if something that is already normally distributed, so a random variable of x is normally distributed, it's just going to make it normally distributed. So I took the height of the students of this survey. As you can see here, when I run my histogram here, you can see that the height of this student is already normally distributed. So when I take a sample size of 30 and I replicate this by 1,000 times, well, you can see what is going to happen here on the first condition. It's just gonna make a more normal distribution. So as you can see, it just made it more normal. Now, another thing you can emphasize here is that when you have a sample size and a population, so here, for example, the population mean and the sample size mean is going to be the same. So what we're saying here practically is what it says here, that if mu of x bar is equals to mu of the population mu. So as you take a sample size and you get in larger, population mean is going to be the same. However, when you take the sample standard deviation, so as you taking the sample standard deviation and then divided by the samples that you're taking, our standard deviation will get smaller. So that's what creates the graph to make it, it's pushing the graph of the outside to the inside to make it more normally distributed. So our population standard deviation and our samples standard deviation is getting smaller, whereas the mean is equals the mean. Now, condition number 2 of the central limit theorem, for example, we talk about for something that is not normal, a random variable of x that is not normally distributed, such as the hours of sleep on this survey. So as I run this, you can see that this is not going to be normal. So here is practically is skewed right. Well, go for the tail. So skewed right, practically. So we're gonna emphasize our central limit theorem here. We're gonna increase the sample size of 30, and then we're gonna replicate this 1,000 times. So this is called bootstrapping. So when I run my sample, for example, when I run my replications for a sample size of 30,000 times, you can see that now our hours of sleep is becoming normal distributed. So another thing to emphasize is that the population mean is equals the sample mean, so that doesn't change that much, so that always remains equal, like we see here in our theorem, that the mu of x bar is equals to mu, so that doesn't change that much. But our new standard deviation here, it's gonna get smaller as the sample size gets larger. As you can see here, our population mean here is 1.48, and when we created our sample size and then divided by n, well, our sample size is getting smaller, but our mean remains the same, and our new standard deviation gets smaller. So I hope that this makes sense now that I did a simulation for you guys in order to better understand our central limit theorem here.